What we're doing now here is just diluting the manure. We're using 2.5 gallons of water to 5 gallons of manure. And as Jay just mentioned, one of the reasons to do this is not only to get it to flow through the system better, but to get the optimal solids percent. And based on some of the preliminary data we have, that this particular dilution rate gives us a solids content of about 8% total solids, which is right around what you want.
So this is the loading tank. So once a week, right now we're doing once a week. We might do it 2 times a week as the temperature gets warmer here in the summer. But right now we have weekly manure additions, 5 gallons manure, 2.5 gallons water in this loading tank here. There's a PVC arm or inlet that flows down into the digester, 6-inch PVC. The digester is a 300-gallon polyethylene tank. The liquid volume in the digester is about 2/3, so there's about 200 gallons of manure and water and whatever else is in the liquid in the digester usually. And then on the outflow is what we call a compensation tank, or the exit tank. So the water flows in the digester, flows through the digester, and eventually comes out in the compensation tank.
Referred to as the compensation tank, and this is basically the exit for the system. And then the other purpose this tank serves is that when the biogas pressure builds up in the system, it'll lift the slurry level in this tank to compensate the pressure in the tank, so it keeps that from building up too high of a pressure in the main reactor tank.
There's like probably 3 main functions. So one of them, you could just think of it as an exit tank. It's just the outflow of the digester, that whatever the digester's done with has to flow out somewhere. But it also holds water in it all the time, so it provides an air or a kind of a water break, which prohibits oxygen from getting back down into the digester. And then the third function, as you build up pressure in the digester, the water level in the compensation tank will rise, and as you remove the gas from the digester, it'll flow back in and gives you that mixing. So it seems like just an exit tank, but it actually serves some more functionality on that. So since there's pressure inside that tank, it's pushing, so there's water inside the tank, and that pressure is actually pushing down on that water. And as it pushes down on the water inside the tank, inside the digester, the water in the 2 arms, on the input arm and the output arm, elevates. So the level inside this compensation tank, we have a meter stick here, so we can record that. So as we build up pressure inside the digester, it pushes the water up on the inflow and the outflow arms. Then when we release the gas from the digester, the water in the inflow and outflow arms will flow back in the digester. And that's a really important feature of these fixed dome digesters, because they're kind of self-mixed. That's another big limitation for digesters, is the mixing of the digester. So many of the kind of higher tech or more mechanistic digesters, there's actually a mechanical mixer that's stirring the digester continuously, which is helping the microbes get to all the nutrients they need within the digester. But in this type of model, there's no mechanism, so it would be cheaper and use less energy. But in the design, it actually allows for it to self-mix a little bit when you load it and when you remove the biogas.
Because the methanogens are such slow-growing organisms, we collect a sample from the spot where their concentration is the highest, and then we return that to the head of the system just to keep the slow-growing population from flushing out too frequently.
So this is a process that's not that common with digesters, but we think it'll help optimize the community of microbes by giving it some positive feedback. And when you look at like wastewater treatment plants, this is a real common process. It's called return activated sludge. So if you look at any type of wastewater treatment plant, they're collecting the sludge from the back end of the plant and move it back to the front end of the plant just to maintain the microbial community. So we're using it here to try to optimize the microbial community.